Bluetooth. Get it straight.
Okay, today we're going to talk about groundwater flow. We're going to develop general groundwater flow equations. This is the first of about 3 groundwater flow lectures, and the rest of the next few weeks we'll be studying groundwater flow, whether it be in aquifer or towards wells that are placed in aquifer. So we'll start by developing the general groundwater flow equation, and then we'll simplify it greatly in this first lecture and begin to look at some one-dimensional flow problems. Confined aquifer and an unconfined aquifer in between stream boundaries. We're looking at section 3.9 and 4.1. Remember, after 3.9 in chapter 3, it becomes soil hydraulics again, so we're just going to skip over that because we've already covered that. So the conservation of mass, together with Darcy's law, is what we're going to use to build our model. Let's refresh our memory on conservation of mass here. Conservation of mass, we have mass coming in over a controlled surface minus mass going out over a controlled surface is equal to the accumulation within the control volume. So in this case, in a one-dimensional case, we'd have a controlled surface here and here. Each of these controlled surfaces would be an area of dA, small representative volumes. And inside, we have the control volume. Control volume is dx dy dz, small control volume. So the mass in is the density, mass per unit volume, times the velocity vector going in across the surface. Basically, mass per volume times velocity times area. Mass in. And the rate of change of time of the mass, again, per unit volume density per unit times the unit volume of the control volume. So mass in minus mass out is this term. The change of mass inside is this term. Let's look at just the change of mass inside, so the accumulation term. So in our aquifer vocabulary, this term would be equal to the gain or loss of water from the control volume due to head change. So there's our specific storage term. There's our head change with time. The rest is just the geometry. Here's the control volume, mass, unit volume. And that would also be equal to any source or sink of water that was happening inside of our control volume. This would mostly be an injection or extraction well if we were having a real groundwater model. For now, let's just call it W and carry it along with us. The change of mass inside the volume is equal to this specific storage-related change, which has to do with the head drop or the head gain, and then any kind of source or sink of water inside the domain. Now let's look at the control surface, and this is just in the x direction, just to keep it simple here. So the water coming in would be equal to the specific discharge at one surface plus the change in that discharge across the distance dx that it's traveling minus the specific discharge on another surface. So remember, the amount of water coming into a piece of aquifer to the specific discharge times the area of that face. The area of the face. So if it's traveling in the dx direction, the area of the face that it's traveling into is dy dz. So put that together, you get that density times these two terms here cancel out. You end up with dx dy dz times density here times the gradient in Darcy velocity. So the left-hand side of the equation is our nomenclature for the flux over the surface of the control volume. The right-hand side are really the in minus the out terms based on specific discharge and density. So if we put that in all 3 dimensions, we would end up with similar terms in the y and z direction. So if we put those 2 things together, accumulation term here and the flow over the surface term here, we have these two expressions that we just developed, and we put them together all on the right-hand side. Notice that we're making them equal to 0. This is conservation of mass. So this says that if you're accounting for what goes into the volume, what comes out of the volume, and you're accounting for any changes within the volume due to head changes or sources and sinks like wells or injection wells or extraction wells, if you're accounting for all that, then everything has to sum to 0. There's no mass created or destroyed here. So if we put those together, we basically end up with this expression from our previous one, where we have this specific storage term, these Darcy velocity terms, and a source sink term here. But it all has to sum to 0. Now Darcy's law comes into the equation because we know what these specific discharges are in terms of head, right? They're equal to the hydraulic conductivity, it's the gradient in head, in the x direction for the x term, y direction for the y term, and z direction for the z term. We can simply substitute these in here for the q, x, q, y, q, z. We do that, you see these new terms in parentheses here. That has brought our Darcy's law into the equation. So here we see the control volume for a piece of aquifer. You can see the characteristics of the aquifer that we've been talking about. The main pressure term is head. Property of the aquifer is the conductivity and the specific storage. So now we make some simplifying assumptions. Don't always make these, but if we don't make these, we probably can't solve them with simple systems. We have to use computer models. There are many computer models that handle this with no simplification, but it's good to start with the simple ones. So first simplification is to say, let's just have a homogeneous aquifer. That means that Kx equals Ky equals Kz. Let's just call it K. It's the same in every direction. We know this is not true in most cases, but it does allow us to make some simple one-dimensional models where it doesn't really matter what Ky and Kz are because you're just working in the x direction. In this case, we get rid of the subscripts here, here, and here, and now we have a K that we can pull out that's in each one of these terms, and we end up with just the K out front. And with the K out front, we can go ahead and take the second derivative, dx of dh dx is now d squared h dx squared. The second derivative of head, or the rate of change of the slope of head in the x direction. How sharp is the gradient? With that, we end up with this term, this equation here, where we have the specific storage divided by conductivity, the source term divided by conductivity. The right-hand side is simply del squared, the second derivative of the head in all three directions. Another simplifying assumption is just use a two-dimensional horizontal aquifer of uniform thickness. We're looking down at an aquifer that is of a thickness B. If we do this, we should recall that storage coefficient is the specific storage times B. So S instead of S sub S. So why do we do that? Well, in a moment you'll see. First, we get rid of this term here because we aren't worried about the Z direction. Second, we put in this B because we are concerned about the thickness of our aquifer. We took this term, S sub S is equal to S over B. Just substitute in here. There's our S over B. So given this, and then we make a new definition of a term where T is the aquifer transmissivity. So transmissivity is basically the conductivity of the aquifer, but it considers the entire thickness of the aquifer. So it's the conductivity over an entire aquifer be thick. Another simplifying assumption that's very common is steady flow conditions. And so in this case, we set the change of head with time to 0. So nothing is changing with time. Head can still change in the different dimensions, but it stays static in its distribution. So flow goes from high to low head, but the high and the low parts are not changing. They're just steady pictures. So in that case, we only have this source sink term balanced by the Laplacian term here, the second derivative. Or if there is no source sink terms, we see our Laplace equation, which we were introduced to before when we were doing flow nets. Okay, let's look at our first simple flow system. So this is a system of a confined aquifer of uniform thickness, and in this case, there's if we're looking at steady flow, then we have the Laplacian equation, but we only have one term. So it's really just an ordinary differential equation, even though it's written as a partial derivative here. And so we can just integrate it twice. And when we integrate that simple term twice, we end up with the equation of a line. So two integration constants, C1 and C2. In order to know what C1 and C2 are, we need to know some other things about our aquifer, and those are usually pretty easily said. We usually know the head levels at the boundaries, such as these wells, so we might know the head levels here and here. And if we call one of them, we could just call this one 0. We could just say this head is 0. This head will come up to be a negative number. That doesn't matter. Still, you'd have flow from high head to low head, so flow would be going in this direction, down in the aquifer, I should say, not up in the above the aquifer. So if we know that head's at 0 at one end, and we know that from Darcy's law, if we rearrange Darcy's law, then the Darcy velocity here, v, I think we were calling it q, so we could call this q as well. But it gets a little confusing in the T&M book. So I think they call it v most of the time. So if we have dh dx is equal to minus specific discharge or Darcy velocity over k, then that's just the slope, and we have the equation of the line where head is going to decrease from left to right here, and it's going to decrease with the slope of Darcy's velocity divided by k. It's very simple. Now, if we have an unconfined aquifer, things are a little bit more tricky. The main difference is that the water table is now a flow line, and it's a nonlinear one. So what we generally do is we make some simplifying assumptions. We say that flow is horizontal and uniform with depth, and that the specific discharge there obeys Darcy's law locally, but maybe not over the entire domain. So Darcy's law is equal on each little piece of the slope here. We have Darcy's law, but we don't have it going exactly from one end to the other end, like here and here. It's a little hard to tell in this figure, but if we connected those lines, it would look something like this if I can draw it straight, not where the dashed line is. So if Darcy's law is good across the whole domain, we would say dH/dL, but it's just good across dH/dx, little pieces at a time here. So these assumptions make the discharge per unit length, which is in the textbook is this little q here. So Darcy's velocity is indeed v. Discharge per unit length is q, little q, which is big Q, the flow rate, divided by the width of the aquifer. And that's going to be equal to k times h. So h is a variable term, small h here, large h here. So h is a function of x. So we have k times h times dh dx. So this is the flow per unit width of the aquifer, thickness, I guess. So if we start with that previous expression and integrate it twice, we will get that, actually just integrating it once, sorry about that. We integrate that once, we will get, remember, a constant of integration c, and we get the h squared term now because we already had this h. So we basically integrated h dh, brought the dx over to the other side and integrated that. We ended up with q times x. So again, in order to know this constant of integration c, we have to know some boundary conditions. We know that h is h0 at one end, it's at h1 at the other end. Everything is steady, nothing's changing at time. So basically we know the two end members of this equation, so we can use those at x equals 0. We plug in a 0, x equals 0 here, and at x equal L, we plug in an L for x, and we solve for the c. And so if we do that, we find we can rearrange the equation. We get that the q is equal to k over 2x times this different in squared head terms. So this is kind of a parabolic type expression, parabola. Hard to write with this little pen, but I'll just call that parabola. This is the Dupuy equation. So this assumptions that got us to this point for the unconfined aquifer are often referred to as the Dupuy assumptions. So it's a simplified depiction of the water table. It's not 100% accurate, but it works pretty well as long as our water tables are relatively flat. In many cases they are, because groundwater gradients don't tend to be super steep. Okay, let's look at one more here. This is the when we have two stream boundaries or two channel boundaries. So in this case, and we also have a new twist on the problem where we add a little recharge to the top of the problem. So this is feeding the groundwater from the above. So if this is unconfined, again, we use the Dupuy assumption. So we can start right off by saying that the Q is a function of x and h, because the h here varies with x, because this surface is curved on top. So we use continuity to say that the recharge must balance with the groundwater flow. So the recharge here is W, the recharge rate, times X. So if we combine these two equations, we end up with an expression that shows that h squared is related to HA, which is one of the boundary conditions. So this is the unknown h, and this is one of the known h. Then we need to know the recharge rate, and then we need to know what distance we are from the boundary. So it's similar to the Dupuy expression with a little bit of a wrinkle, this recharge rate. Then the base flow entering the stream channel from the aquifer is QB. So this could be the groundwater feeding the stream. When it's not raining, the stream is still often being fed by groundwater, and that keeps it going. So that would be given by this 2 times A times the recharge rate. So a couple of easy problems there, easy models, but they begin to give you an idea of the difference between a confined aquifer and an unconfined aquifer, and some of the dynamics, very simplistic dynamics of recharge feeding a stream. But it all is based on this conservation of mass with a little bit of Darcy's law and specific storage thrown in to make our control volume an aquifer instead of a empty reactor. So I hope you found that interesting, and we'll do some problems on that in the upcoming homework number 6, and I'll have a couple of practice ones that we can do on Tuesday.